Good morning. Welcome to the today's class. So, last class we just discussed about the machine independent assembler features, in which we have seen this literals, and then literals can be the character or hexadecimal constants or string constants, which can directly be specified in the instruction using is equal to symbol. So, which is going to be allocated memory by specifying in a specific place by using LTORD. If not specified, it is going to be default allocated at the end of your declarations. So this is one use of literals, which is directly using the character constants and string constants in the instruction itself, just similar to our immediate addressing. And then we have seen the symbol defining statements. We can define the symbol without declaring them by specifying the name and followed by assembly directory UTU and a value. So which is going to make an entry of this user defined name in the symbol table and then the value in the symbol table, which is going to be the constants. Either it can be an integer constants or it can also be a what you call expressions, which can evaluate into a value. This also we have seen. And then org statement, org reinitializes your location counter value to the specified value. So if at all you want to categorize your program somewhere, the instructions and someplace, the what you call declarative statements and all, you can reinitialize the location counter by using org statement with a value. Org can be used without a value, then the location counter is initialized to or continued with the previous case, whatever the previous value was there, it is going to be continued. So this and all are some of the additional facilities what we have, which we call it as machine independent features of assembler, right? Okay. And then we have also seen the expressions. Expressions are way of specifying. It's specified by using EQU assembler directory itself. But on the RHS of EQU, it's not required to be only the value. It can also be a mathematical expression which will be evaluated and the value will be used. As being told, the expressions can be of two types, which may be either relative or it may be what you call absolute expression. If the expression evaluates relevant to the starting address of the program, we call them as relative expressions. If the expressions evaluate into a value which is not dependent on the starting address of the program, then we call it as absolute expressions. Yeah, in the example we have seen return address as a declaration of one word and length as a declaration of one word, and buffer as a declaration of 1000 words, and buffer end equal to the current position of the location counter, whatever the current value of the location counter will be. And the max length is again a symbol defining statement whose value is evaluated by subtracting the buffer value by buffer end value, right? We have seen the implementation also. Yeah, expressions can be absolute and relative. This we have discussed, and how this one will work. Yeah, return address is allocated the address 0030. So length is allocated the address 0033 because they are just reserved words. Each word consumes so 3 bytes. So for that reason, reserved word, if it gets a address at 0030, length will going to get the address at 0033. Buffer will going to get the next address at 0036. And buffer is consuming 1000 bytes, so the next address of buffer will going to be 1036. And max length will be evaluated as buffer end minus buffer, so it will going to yield you 1000 as a value. So among them, return address, length, buffer, buffer end, all of them are relative expressions because they are evaluated with concern to or relative to the starting address of the program or location counter. But the max length is evaluated by subtracting the buffer end, buffer value from buffer end. So it is giving you an absolute value, that is 1000. So it is called as an absolute expression. These things we discussed yesterday in detail. Yeah, we proceed further. We also discussed the program blocks, I think so, which is logically partitioning the different parts of the program within the same file. Please remember, within the same file. If it is in a different file, then we call it as a control section. Then the linker will come into picture. But here within the same file, so the linker issue will not. So we can define the program blocks separately by giving them by an assembler directive use. We use assembler directive use and specify the block name. So there again your location counter will be initialized to the zeros, so that indicating that this is a new block. Once after all the program is written, in a pass one of the assembler, your pass one assembler will going to take the different parts or different parts of the same block, and we're going to give a continuous address. So that's how the uniting of the programming block or bringing the same blocks or the instructions belonging to the same blocks together will happen in the pass one of your assembler. Okay, and the assembler directive use starts with the use followed by the block name. The block name may be any name that the user can give, which is going to initialize your location counter to the 000 value. And if the same block, if the use assembler directive is used, so without the block name, the instructions will belong to the default block. So that's how we're going to be specified. Yeah, we have seen an example yesterday, but we hurried up. We can now understand it level by level. The name of the program is copied and the start address is given as 0000. So means to say the first instruction should start at the address 0000. So we have three consecutive instructions. See, by default, any program will have one block that is called as default. If you want additional blocks, the user should use the assembler directive use and specify the block. That's how it works. If the none of this use assembler directive is present in your program, then the entire program will be written in a single block. So it is up to you to partition the program logically so as to specify the program blocks. Here we have used by default, the first block is a default block which contains three statements: LDX, LDA, STL, right? And next we are specifying use C data. C data is a new block which we are specifying, which is again containing the three instructions. See, there we are restarting our address starting from 00006 like this. And after that, we have just used the assembler directive use without specifying any name. Means to say the following statement should belong to the default block. Okay, and then after some statements, we have again an assembler directive use followed by C block, which again below that is containing two instructions, clear X and clear T, which is belonging now to a new block called as C block. Totally here we have three blocks. One is default, one is C data, one is C block. And followed by that we have again use, which is putting the next two statements below that into the default block. So default block is having 1, 2, and 3 parts. Apart from that, C data is having one part and C block is having one part. So now once after we do, every time when you see the use, the location counter will be initialized to 0 and it is going to continue with the previous address of the block like that. And all these blocks are going to be entered into the symbol table along with their addresses like that. During pass one, you can see this is what is the outcome, what we're going to get after the pass one, which is marked in a blue background. That's what is the outcome after the first pass of your assembler. In the first pass of your assembler, it has accumulated three parts of your default block. That is, three instructions starting from LDX and two instructions starting from LDCH, HDCH, and two instructions, one instruction STA. All these things are put together and in a continuous address. We can see that default block starts from 0000 and ends at 000F. Similarly, the C data is the next program block which continues with the last address of default block, that is 000F. The 3 bytes from there will going to be 0012. So C data will going to start from 0012, which has got the instruction length, alpha, and return address declarations, which is allocated memory continuously with 3 bytes each. And after that, we are giving the memory for our C block, which is another program block that is containing two instructions, clear X and clear T. Actually, clear X and clear T. So this is given the addresses just after the C data. Now it is nothing but the entire thing is going to be a 3 consecutive set of instructions written in a continuous manner. So for that reason, after pass 1, the pass 2 is going to take up this as a single program and going to assemble it. So if you ask what is the use of it, it's just makes the program or the task easy to specify the different instructions belonging to the same block at different places. So you can logically partition the program and which can improve the readability and which can give the clear understanding of the program. Apart from that, the mechanism of assembling or linking will not be affected anyway by using the program. So this is one of the desirable feature that is being introduced in the machine independent assembler features, right? So your assembler is capable of rearranging the instructions belonging to the same block during pass 1 of the assembly. So this is the concept about program blocks which we discussed yesterday, and we shall continue today. Yeah, and this symbol table entry will also be made. Yeah, you can see that default block is starting at 0000 and ending at 00. Similarly, the C data block is starting at 0012, ends at 18, and C block is starting at 0018 and ends at 1E. So this gives an idea for your is anyway the pass 1 itself is the pass which is going to make the entry of all the user defined symbols into the symbol table. So anything that is appearing towards the LHS, the same rule applies, nothing changes there. So default C data and C block are the user defined symbols which are appearing on the left hand side. So we are making the entry into the symbol table that it is a symbol, which helps us to recognize each block size. Fine. We shall proceed now. Next, we have something called as control section. Yeah, majority of the times they may ask you the difference between program blocks and control section. Program blocks is logically partitioning the program within the same source file into the different blocks. That is done by using the assembler directive use. Control sections are the parts of the program written in separate source files. Please understand, the part of the program written in different file is called as control section. So same source program written in different files. This we can do it in any programming language. Even in C programming language, you can use external variables and use those variables in source program written in other files. For example, if your program needs 3 functions, you can write each function in different files and main function in a different file. Only thing is that while compiling, you should compile all these 3 together into a single object code file. That's all. So GCC main.c, function1.c, function2.c, function3.c. So together all of them creates one a.o. Same is what we call it as control sections. Say source program, part of the source program written in different files is going to be called as control sections. Each file contents will going to become one control section. Getting the idea? Each source program, I mean each part of the source program, each file will going to be called as a control section. And here, so as to evaluate it, so it may so happen that you have one variable that is defined in one file, file 1, that may be used by the part of the program that is written in file 2, or maybe in file 3. Or it may so happen that file 1 will going to use the variables that is declared in file 2 or file 3. So this should be handled. This cannot be handled by your assembler because it is not the symbol defined in your source. It is so the symbol that is defined in other source file, but you are referring it. So as to handle this, the source files are assembled separately and then linked together. That's how internally, even in C programming, it is going to happen. The control section may need to refer the variables and constants that is defined in other control sections. That means the source file returning other files. This sort of references are called external references, and these external references are handled by two assembler directives. Be careful with this. One is assembler directive, we call it as extdef. The extdef indicates the symbol defined in this control section, means in this file, but it is referred by some other file. May be referred in this file. If it is referred in this file, it doesn't affect you. But if it is defined here and it is referred in some other control section, that should be marked as extdef. This is an indication not to your assembler but to your linker that this is a reference to the variable or constant defined in this file but will be used by someone else. So it should be made available, its address should be made available across the control sections. Similarly, one more assembler directive we have, which is called as extref, which is external reference, means you are using in this section, but it is not defined in this section, but it is defined in some other control section. That's what we mean by external reference. Used in this section, defined in some other control section is called as external reference. extdef means defined in this section, but may be used, may not be used in this section, but maybe will be used by some other control section is what we call it as extdef. These two assembler directives indicates the linker to resolve this external variables which is defined in one section and used in other section. So how exactly this works, we'll see with an example. Yeah. See, we have a program here. The program, what it does, don't have the logic much used, but observe the program. Copy is the name of the program, start, and it is starting with 0. And at the beginning of the program itself, we are using these two assembler directives, extdef and extref. Which are extdef means defined here, used somewhere else, is buffer end, length. These are the three variables defined in this section, but may be used in other sections. extref is rd, rec, wr, rec, which are the two variables which are not defined in this section but defined in other section. Fine. Something like that, we are having STL, return address, means return address is declared in this section only but not used by any other section. So for that reason, we are not putting it under extdef. Fine. You can see that below we have a declaration of resw1 return address. Return address is declared as a one word integer. So that value we are putting it into the L register. Fine. That's the first instruction. Next instruction, what we have is a format 4 instruction. How can I make out? Because there is a plus in front of the instruction. It is a format 4 instruction. Jump subroutine read rec, and you see read rec is an external reference. Means to say it is not defined in this section but defined somewhere else. But defined somewhere else in any other control section. And remember, all the external references when we are making, which is not defined here, defined somewhere else, we cannot use the displacement. We cannot use PC relative, we cannot use base relative, nor we cannot use immediate addressing. We must and should specify the complete address. Then only it is possible to resolve. So that's why for all the external references between the control sections, we will go for format 4 instruction. No format 3, no format 2. Fine. We must and should go for format 4 instruction. Then only we are able to resolve the complete address. Replace the reference by an address in some other section. Fine. Then we have LDA length, etc., 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 and the program goes on. And at the later part of the program, we have JSUB. Again, it is a format 4 instruction, and we are giving the operand as WR-REC, which is also an external reference. You can see that in extref we have these two references, RED-REC and WR-REC, right? And we have a declaration of return address, we have a declaration of buff, and we have a declaration of buffer end, and we have a declaration of length. These and all are defined in this section. This is my first control section. Majority of the programs will have only one control section, but in this program we have multiple control sections. We shall see the next part of it. So we have other control section. The control section name, you can see that I have put a dot, and I have written REC control section. A dot front of some writing in SIC or SIC program indicates that it is a comment step. A read record is a control section which is having no external definitions, but it is having external references. What are the external references it has? It has got a buff, end, and length, which are being declared in the default control section. And what it is doing? It is doing clear and LDT with buffer end. Again, its LDT is a format 4 instruction because it is having an external reference. HTCH is also a format 4 instruction which is using the buff, right, like this way. So these two variables, buff end and buff, are declared in default control section, but it is used here. So for that reason, the declaration means we are using format 4 instruction and also specifying that it is external reference. Similarly, we have one more control section. That control section we are calling it as WRREC control section. The same thing here also. We have buff and length are two external references what we have, and LDT length, and we have buff from X, like this way we have, and these two are also external references. So we are using format 4 instruction. Fine. So totally we have 3 control section: one default control section, one read record, and one write record. Now these 3 control sections are assembled separately. And what happens during the assembly? All the external references are handled. All the external references instructions must be format 4. I specified why, because we need the complete address. We cannot specify the displacement. Format 3 can only specify the displacement, that's possibly used with only the code written within the same control section or within only the single source file. But now it is not possible, so we need to specify the complete format 4 instruction. The operand of the instruction is external reference. The operand address is marked 0000. For example, here in the default section, plus JSub read record or plus JSub write record, or in the read record control section plus LDT plus STCH. In the next one, we have plus LDT and plus LDC. These are all, when assembler goes through them, it can allocate address for the instructions, but it cannot allocate the addresses for the operands because they all are the external references. They are present in some other control section. For that reason, when we are assembling these instructions, the address for them is marked as 0000. Why? Once the address is got, original address is got from the concerned control sections, then we need to modify those addresses, and the complete address need to be modified. That's what is the thing. Fine. So, for example, here plus JSub read record, JSub replaced by its opcode, but read record value will be marked as 0000. Right. After the assembly, it is informed to the linkers. Take care of these particular references, external references. To whom? To the linker. So, and how to specify the linker that these specific address need to be modified? That is by using modification record. I told you about this modification record earlier also during program reallocation. There also I made you clear that the modification records during the reallocation of the program is written only when the program contains format 4 instruction, and only for format 4 instruction. Format 3 instructions are always contains the displacement, so there is no need to write the modification record. Modification record is only need to be written for the format 4 instructions so as to resolve the reallocation, that is by your load address, or it may be due to the external references due to your control sections. This is what happens. And the modification record, as usual, column 1 contains M indicating it is a modification record, 2 to 7 indicating the starting address of the field to be modified. And here starting address is not the address of the instruction, it's the starting address of your operand. Remember the starting address of the operand. And the length is specified in half. So for 20 bits, we're going to use 5 bits. For 20 bits of entire address, we're going to use 5 bits. That is, 5 fours are 20. Half bytes is going to be used. Fine. Okay. And we are also specify plus or minus, because the control section 1 may be assembled first, 2 may be given address first. This may happen. So for that reason, we may either need to add or either we may need to subtract the starting address. And usually it is going to be add for your default control section, and it is going to be a subtract for all other control sections. So like this way. Right? See the example on column 11 to 16 is the external symbol whose value to be added. See, for example, if it is a read record or write record control section, the value of default section should be added or subtracted. Or if it is a read record or control section, the value of the default should be subtracted, something like that. Okay. Yeah, for example, here for the default section where we have JSON read record, the read record starting address is supposed to be added to whom? To the operand specified in the JSON, correct? No? So the address of JSON is 0004, and the bits that is supposed to be modified. Because why I am telling 0004? Because the instruction starts at 0003. 1 byte next to that, that is 0004, and the next 20 bits need to be replaced, specified in half bytes. That is your file. Whose address that is to be taken? The return address that is to be taken. That address should be added. That's what the simple modification record is specified. And this reallocation, just like in the program reallocation, it is done during loading and linking. Here also it will be conducted by your loader and linker. Fine. So that's how the external references is handled between the control sections. This and all, something like the additional features what we are doing. You can write the entire program in a single source file, but now you have a provision of writing the source file in multiples, so program in a multiple source file, and also specifying the variables that is used. So this is the same feature what we do have in our C programming by using external variable, wherein you can use a single variable, and where you are not using extdf, extref, but once the variable is specified as extref, it becomes a global variable for all the programs written in multiple source files, and it can modify, update to the same variable, but you're going to have the value. So that is handled by the linker of the of your GCC. But now it is specifically your assembler is doing this. Your assembler is just assembling. Your linker is doing the linkage of external definitions and external references. So this is one of the major concepts, controls. And usually in the exam, they're going to ask you the difference between program blocks and control section. The logical partitioning of the source program within the same source file is your program blocks, and physical partition of your source program into multiple files and resolving the external definitions and references is what we call it as control sections. So one of the differences that they will be usually asked, you can write it with an example, a small program example you can take and get it. Right. And if we use the assembler directive use in the case of what you call program blocks, but here there is no assembler directive. Program will be written in multiple source files, and we use the modification record so as to specify the addresses that need to be altered accordingly. Fine with this? So this is one of the major concepts, repeatedly asked concepts. Right. Next we have assembler design option, a small part we are going to discuss. And almost we have come to the end of module 1. We have one more small concept that anyway we are going to discuss on Saturday, that is called as your macroprocessors. And that ends up your, what you call, fine. That is your module 1, that is SIC and assemblers. Yeah. We have design options that till now we have seen 2 pass assemblers, which take 1 pass to allocate addresses, that is definition, and 1 more pass to resolve the operands, that is convert the operand means mnemonics to opcode and operand to its addresses. Why can't we implement a 1 pass assembler? Can't it do it in a single pass? Yes, it can do it. These assemblers, one pass assemblers generate the object code in a single pass, only one pass, and everything is resolved. But to implement this, the problem with the program is that we are not doing the declarations and at the beginning, so we don't get the addresses. We don't get the entries into the symbol table. Now, we are doing the declaration at the end of the program. That's the problem. The problem is with the forward references of the symbols are not defined. So how can we handle that? One way, hence we have two design options for one pass assembler. Both, both options does the same thing. It needs all the variables and the constants need to be, and even your symbol defining statements should be defined at the beginning of the program. Then the instruction should follow. That's how we need to do it. But one type of one pass assembler, we call it as load and go, which is like an interpreter, which is like your interpreter. The entire program is brought into memory. It will be assembled, and it will be executed. So it's like an interpreter. It's not like a compiler, so which will going to write it. This assemble leads all the user-defined symbols to be defined before use. Forward reference due to the jumps. If at all, I need to jump ahead. So I have got something like return loop, and the loop appears somewhere later. I'll go to get the address of loops later on. So for that reason, those references, those sort of jump instruction found the opcode. For the opcode is generated for the mnemonic, and the operand is kept blank. And when the operand you get, you're going to make an entry into the symbol table in all the places where and all those loop is appearing. Please try to visualize this. Suppose I haven't taken any example here, so that's why I'm very you. At 0003, I have JMP loop, and the loop is appearing at 0036. So I get the address of the loop 0036 only when I reach 0036. Until that, this operand address or this label, which is appearing on RHS, is kept blank. Once the loop address is entered into the symbol table, we are going to make the correction for this particular operand address. That's what we call it as load and go assemblers. Advantages can be used in the slow machine where the external storages is not there, and the assembler generates the object code and executes immediately. Everything happens in memory. So every time you need to keep on assembling if at all you want to use it. A variant of this we have is again a one pass assembler, but which writes the object. What it does, the assembler generates the object code in one pass. Assembler needs all the user defined symbols need to be defined before everything is done. Generates the object code and writes it into the object code file format, which is containing the header record, text record, int record, all those things. So it handles the forward jumps using a text record. What it does, if the jump instruction is found, opcode is generated for the mnemonic, operand is kept blank in your text record. So while writing in your object code file, text record, that address is marked as 000. When that operand appears or when that symbol gets the address, these 000 will be replaced by the new address. Means for rewriting only those places where the addresses is having forward references, we must go back and do it, or otherwise it is not. So this is the second design option of one pass assembler. Two types of one pass assemblers we have: load and go, and then another one is writing the object code to the file format. This is one design option. We have another design option, multi-pass assembler, which is going to see it in the next class, and also complete with what you call the macro process. Fine. Thank you. That's all for today. We'll stop here. Fine.